All right, guys, so this is going to be 1, 2, 3 for Algebra 2. So today we're actually going to start trying to look at linear relationships. So pull this up, there we go. All right, so you've seen this in X plus B form a lot in the past. So first of all, I just want you to kind of go through number 98 here to try and answer those as best you can. You don't have to write them down, but just kind of in your head answer those questions to yourself, and then come back and we'll talk about those. We'll see kind of how what you came up with relates to what I'm going to be talking about. Okay, so part A here. What do x and f of x represent in the function? What do m and b represent in the function? Which ones can you change? So x is kind of your independent variable, and f of x is also like your y, and that's your dependent variable. So those are the kind of inputs and the outputs. M and b, M, you'll typically call it the slope or the rate of change, all those kinds of terms. You're going to hear me try and say rate of change more and more and more, because rate of change is more of what it's used for in the real world. Slope is just purely almost a mathematical only kind of term, which we use for that kind of value. And then B is like your initial point or your starting point, or you may also know it as the y-intercept as far as the graphical representation means. So the x's and the y's, or the x and the f of x, those are things which are going to change depending on the value, because there's a whole set of pairs of x's and y's which make one particular equation or statement true. M and B, those can be different, but they can't be different for a function, right? Once you have your function, your m and your b are the things you set that kind of define what your linear function is going to look like. So we can kind of plug into different values of m, different values of b. You can do that on Desmos, things like that. I assume at this point you're fairly comfortable with what different linear graphs are going to be looking like, but if you would like, you can explore that a little bit. They want to introduce the ideas of parameters and variables. Variables, you've heard that term a bunch. That's like your x and your y. Most people think of variables as just being a letter in the middle of a math problem, right? But a variable has to be a thing which can change, right? A parameter is something that is kind of fixed in a sense. So a parameter can also be represented with a letter, like m and b are actually parameters. The reason why we use a letter for that particular parameter is because it's going to be different for each linear problem. So y equals mx plus b is our kind of general form for any line. But if I were to say y equals 2x minus 5, that is the equation for one specific line. And the variables in that line would be the y and the x, where the parameters would be the m value and the b value. No one's going to get mad at you if you call a parameter a variable. Just trying to be really technical and precise on what these values actually mean. And if I say something like a parameter, I want you to kind of know, hey, it's that kind of number part of the equation, which is kind of fixed for that particular equation. And these give us what are called families of functions, because all linear functions, they're all lines which we can kind of change in different ways. We can make the slope different. We can move it up and down, left and right. We can kind of move it, but they're all lines, so they're all kind of in the same family because they all have that same base thing. We can just change the parameters within that particular family. All right, so number 99, again, I want you guys to pause and try this out on your own. Take a look at what is common between all of those, and then come back and I'll kind of go through it. All right, so this first one on part A, if it's a lot easier to see what's going on here if you change all of those into y is equal to mx plus b form. And if you do that, you should see a very common similarity, though, in that all of those have the same value m, the same rate of change, but they'll have different values of b, or initial points, or y-intercepts. So what that would look like graphically is that those would all be parallel lines with different y-intercepts. So those are, again, in the same function family. Now let's go over to B. On B, if we do the same thing here and we get all of these into y equals mx plus b form, we're going to see we can get them all in that y equals mx plus b form, but they're all going to have different slopes, different intercepts. They're all going to be looking different in various ways here. Or sorry, all having the same y-intercept. So those ones all share the B parameter, but have different M parameters there. So again, those are, again, still a family of functions, because they're all still lines, but they all kind of share that B parameter as A. They all share the M parameter on those ones. All right, so number 100 here, again, I'll explain it, and then I want you guys to pause it and try it out on your own. You're going to be trying to look at these and determine from the situation or the output table, is this a linear or is this some other kind of relationship? So remember that linear it's that kind of constant rate of change. And if it's not, then it's going to be a nonlinear. Now, don't worry about what kind of nonlinear it is. If you think you might know it, awesome. Go ahead and try and guess that. But don't feel like you have to on these ones here. So again, pause it, try it out on your own. Okay, so if we go through these, some strategies which we could look at. So on the very first one here, on part A, at 0 on our input, we have 0 on our output, great. So then at 1 on our input, we have 5 on our output. So a change in 1 on our input gave us a change of 5 on our output. Now that change has to be consistent for the entire problem for it to be linear. So then from 1 to 2, that's going up 1. I go up 5 on my output, great. Then 2 to 3, I go up 5 on my output, great. From 3 to 4, I go up 5 on my output, great. That's obviously going to be linear because I have the same constant rate of change all throughout every single part of that table. All right, so on B, Killer Fried Chicken charges $7 for a basic bucket of chicken and 50 cents for each additional piece. The input of is the number of extra pieces of chicken ordered, and the output is the total cost of the order. So if I were to order one extra piece, it would be $7.50. 2 extra pieces, that's $8. 3 extra pieces, that's $8.50. So every extra piece is an increase of 50 cents, right? So that's constant no matter how many extra pieces of chicken that I get, right? If they said stuff like, hey, your first 2 extra pieces are 50 cents more, and then past that it's $1 more, then hey, that's not going to be linear because it's going to be changing as I can move forward there. So, but that one is going to be linear because it's that constant rate based on the same change. So you look at number C. So C, I'm going from 10 to 5, causes my output to go from 0 to 5. Okay, so going down 5 increases me by 5. Okay, and then if I go from 5 to 3, I'm decreasing by 2, and then I'm also on my outputs increasing by 2. Okay, and then if I decrease by 1, going 3 to 2, I increase by 1, going from 7 to 8, and then decrease by 1, I go up 1 from 8 to 9, decrease by 1, I go up 1, 9 to 10. So they're trying to throw you off by having the x's not be evenly spaced out, but this is why we kind of do what's called finding a unit rate of change, right? And this is typically what we call slope, is just a unit rate of change. It's how much do I change my output if I change my input by 1. So it's really easy to see that from 3 to 2, from 2 to 1, from 1 to 0. But from 5 to like 10 or 10 to 5, I should say it's a little bit harder to kind of see that. So we can convert that. 10 to 5 is a change of 5. 0 to 5 is a change of 5. So that's a 5 to 5 change. So it's kind of that 1 to 1. And then 2 to 1 and 8 to 9 is again a 1 to 1 change. It's one's going down and one's going up, but it's still that common change there. So that one will also be linear for us. On D, x is at 10, our y is 1, x is 5, our y is 2. So a decrease of 5 on our x gave us an increase of 1 on our y. Okay, so if I were to do a unit change, a decrease of 1 on my x should give me a increase of 1/5 or 0.2 on my y. Now if I go down to 5 to 4, that's a decrease of 1. Now that caused me an increase of 0.5, where it should have been an increase of 0.2 if it was linear. Now right there, I know I'm not linear because I found one counter example for it. I could keep on doing more, but if it's not linear everywhere, it's not linear, because linear is the same anywhere on it. So that one's not going to be linear for us. Now let's take a look at E. So E, James planted a bush in his yard. The year he planted it, the bush produced 17 flowers. Each year the branches on the bush split, so the number of flowers doubles. The input is the year after planting, and the output is the number of flowers. So key term there is it's doubling, right? So if I make it easier numbers, first year I have 1, second year I have 2, third year I have 4, fourth year I have 8, and then I have 16. That's not linear, right? If I'm doubling, I'm going to be getting bigger really, really fast. That's going to be exponential for me, not actually linear, which is key term there. Being doubling just kind of gives it away that's not going to be linear for us. And then taking a look at number or letter F here. I go 0 to 2, takes me from -7 to -2. So increasing my x by 2 increased my y by 5. And then going from 2 to 4, increasing my x by 2 again. That also increases my y by 5, going from -2 to 3. Increasing my x from 4 to 6 takes me from 3 to 8, which is again 2 on my input, gives me 5 on my output. And then 6 to 8 on my x, which is again an increase of 2, gives me 8 to 13, which is an increase of 5 on my output. So I'm consistent throughout all of those. It's going to be linear on that one as well. All right, so let's wrap it up here. So for 101, you can create your own. Try to figure out, hey, what would a situation be that is linear? Either a table or a story. Try and make one that's not stupidly basic, like 1, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Try to do something that has different values of x, and what would the outputs be, or the changes in x are not consistent. Try and do something along those lines. All right, and then to round off here, number 102, without using a graph to decide whether the relationship shown on the table on the right is linear, write a clear summary statement for each of your ideas. Okay, so I haven't been graphing any of these just because it's really easy just to graph stuff and look at it, but that is one additional strategy which you can use. But for this one, let's kind of analyze it as we know. So at 1, we're at 0.5. Okay. So then from 1 to 4, that's an increase of 3. And that takes me from 0.5 to -7. So that is a decrease of 7.5. So every change of 3 gave me a decrease of 7.5. And then going from 4 to 10, that's an increase of 6. So that should be double what my change was from 1 to 4, right? So from 1 to 4, I decreased by 7.5. So I should then be decreasing by 15. And -7 to -22 is a decrease of 15. So that is staying consistent there, right? And then from 10 to 5, again, that's a change of 5, which is going to be an entirely different number for us. We're going from -22 to -34.5. So it's likely correct, but let's try and figure out how we can check that. Now, this is the idea that I mentioned. We want that unit rate of change. So I'm actually going to pull up my document camera here real quick. Let's try and analyze this. Okay, so when I went from 1 to 4, and then we had on the side we had 0.5 and -7. So this had a change of 3. This had a change of -7.5. So I went down 7.5 per 3 units changed, right? So that is how much my y is changing over this number of x's, right? So if I reduce this, right, it's -7.5 per 3, right? If I reduce this down to being over 1, that's a unit rate of change. Well, so how I get here to here is I literally just take -7.5 and I divide it by 3. So -7.5 divided by 3, I get -2.5. That's hard to see in the glare, right? So then that's going to be -2.5 per 1, or just -2.5. That's called a unit rate of change. So every change by 1 in my x should change by that in my y. That's typically just kind of what we call slope, right? So then if I changed by 5 from 10 to 15, well, I want to change negative 2.5, but 5 times, oops, you can't see that. That's 12.5 as my change. And if I go back over here, I'm seeing I'm going from negative 22. If I go down, or if I take off 12.5 more, I'm at 34.5, which is what we got there. So we've confirmed that by kind of going to that unit rate of change, which is, again, a very important thing, and it's typically what we just end up calling slope. And that's also, as you probably noticed, where that whole rise over run thing comes from. Oops, that's the wrong view, right? This was just my change in my y, or I'll call it delta y, over this my change in my x, or my delta x, right? And that's kind of what we end up calling slope. How my y changes over how my x changes will reduce to what we just call the slope. So nothing there is brand new. It just may be a different way of kind of approaching it or viewing it that you may not have thought of or seen in the past. Okay, so on your own here, just kind of answer to yourself, how can you recognize if a relationship is linear by looking at either a table or by looking at a situation? Try and answer that for yourself. Once you're good, here is our homework for tonight. So we're going to be doing 104 through 110, and that'll be it for 1, 2, 3. I'll talk to you guys next time.